Now I'm going to complete the example from lesson 29 of CE 474 at the Air Force Academy dealing with minimum eccentricity. This is our first design problem of a reinforced concrete column, and we're going to start off simple by assuming there's going to be no moment the column has to resist. Its only job is to resist an axial force of 350 kips. This is not exactly common, but it's the first step in our design process. So like any design process, our overarching goal is to make sure that our factored axial load effects are less than or equal to our axial strength of our column. So Pu has got to be less than or equal to phi Pn. And here, phi Pn max is going to equal 350 kips, and that's given. So we'll start with equation 10-2 from our ACI code, which says phi Pn max is equal to 0.80 times phi times 0.85 F prime C times area gross minus area of steel plus Fy times AST. So to explain, the 0.8 is due to accidental eccentricity. There's a phi factor. The 0.85 F prime C times area gross minus area steel is the force in the concrete, and Fy times AST is the force in the steel. And again, this is equation 10-2. Unfortunately, there are two unknowns, area gross and area steel. We haven't designed yet. So let's see if we can determine, maybe reduce those number of unknowns to just one. So we do know that the area steel is equal to rho gross times area gross. That's the fundamental relationship that says rho is equal to area steel over gross area. So we can rephrase equation 10-2 as follows. Phi Pn max is equal to 0.80 phi times 0.85 F prime C times area gross minus rho g Ag plus Fy times rho g Ag. Well, unfortunately we still have two unknowns now. Now it's rho g and area gross. But here's where we have some leeway as a designer. We can assume a starting value for rho gross. If you recall, ACI 10.9.1 gives us a range of minimum and maximum steel ratios. And it says that rho gross has to be between 1 and 8%. 1% is a limit based on shrink and creepage. 8% is the max limit based on constructability. Anything more than 8% gets very difficult to construct. So we'll start off by making an assumption, and we'll assume rho gross is equal to 3%. Closer to the 1% than the 8% is more common, so we'll just go with 3%. And then we'll set Pu equal to phi Pn. So we'll say 350 kips is equal to 0.80 times our phi, which for compression controlled members is 0.65. We know it's compression controlled because there's no moment, and if there's no moment, if you think back to our beam column interaction curves, we're all the way on the left or the vertical axis. We're in the compression controlled region, and phi is 0.65. Multiply that by 0.85 times F prime C for KSI times area gross minus 3% of area gross plus 60 KSI, the yield strength of steel, times 0.03 of the area gross. And we can solve for our single unknown finally, which is area gross, and we get area gross is equal to 132 inches squared. We also know rho gross, so we can solve for area steel. Area steel is equal to rho gross times area gross equals 0.03 times 132 square inches, which equals 3.96 inches squared. Okay, so what we can do now is go back to our design requirements. It's supposed to be a square column. So if we have a requirement of 3.96 square inches, we know it's a square column. The minimum number of bars in a square is 4. So luckily we're right about 1 square inch per bar if we use the minimum number of bars. And for now we can assume number 9 bars, which is 1 square inch each. So we'll say try for number 9s with an area of steel equal to 4.0 inches squared. Now the B required, since it's a square, is the square root of the area gross, which is square root of 132 inches squared, which is equal to 11.49 inches. Therefore, use a 12 by 12 inch column. Just like in our beam design, we had some leeway we could round up or round down. Likewise, we have some leeway in our columns. I've rounded up slightly in our area steel and rounded up again in the dimensions of our concrete. Keep in mind we want to use even inches in our column, so we'll round up to 12. Next thing we have to address, besides the number and size of bars and the dimensions of our concrete column, are the ties. So looking to ACI 71051, for number 9 bars, we can use a number 3 tie. In fact, if we had up to number 10 bars, we could still use a number 3 tie. So for ties, we'll use number 3 bars. Looking to 71052, that section gives us the spacing, the maximum spacing for these ties. And this spacing is going to be vertically along the height of our column. So according to 71052, S, the spacing of the tie, max, is equal to the minimum of 3 things. 16 times the diameter of the bar, at the longitudinal bar, in this case we're using number 9s, or 48 times the diameter of the ties, or B, the outer dimension of the column itself. So 16 dB is going to be 16 times 1.128 inches, which is 18.05 inches. 48 times the diameter of the tie is 48 times 0.375 inches, or 18 inches flat. And B we just solved for, and that was 12 inches. So we're using the minimum of these 3. This governs. So our tie spacing is going to be 12 inches. Now we have everything we need to design: the longitudinal bars in the column, the tie size, the tie spacing, and the outer dimensions of the concrete. We're just going to do a check now using our actual numbers. So check phi PN. Phi PN is equal to 0.80 times 0.65 times 0.85 times 4 KSI times 144 inches squared minus 4 inches squared, or the gross area minus the area of the steel, plus 60 KSI times 4 inches squared, and we get phi Pn equals 372 kips, which is greater than Pu, which was 350 as the given information. Therefore, we're okay. Now our final design drawing would be something like this, where we would show our square column, we would show our 4 bars, we would show the tie around those 4 bars, and we would label the outside dimensions, 12 inches by 12 inches. We're going to label the size of the rebar. So we'll say 4 number 9s. We're also going to label the tie. We'll say number 3 ties at 12-inch spacing. Also, we're going to need the material strength to be able to build this, so off to the side we'll label F prime C is 4 KSI, Fy is 60 KSI, and then finally we'll label our cover, and we'll say 1.5 inches CLR for clear, and in parentheses typical TYP to denote that it's 1.5 inches or interior exposure all the way around. So this concludes our initial design of a concrete column, assuming no moment, just axial load. We've had to choose the number and quantity of longitudinal bars, the exterior dimensions of the column, and the tie size and tie spacing. This concludes this example.